Hi, this is Sid Meyer. I'm doing my quiz for retake, and yeah, let's begin. So first off, we have number 1, which is asking us whether combusting a marshmallow is an endothermic or an exothermic reaction. Well, first let's define these terms. An endothermic reaction means that a system, the energy in the system is being absorbed from its surroundings, while an exothermic reaction means that energy is being released from the system. In this case, a marshmallow being set on fire has energy releasing from the system. Yeah, it's releasing heat and light, meaning that it's an exothermic reaction. So for number 1, we have exothermic because energy is being released from the system. Yes, energy is exiting the system basically. For B, they want us to draw an energy diagram for the values. So first, let's set up our chart. We have our y-axis, which is going to represent, the energy in the system. And then your x-axis is, oh, sorry, can you see that? Yeah. Your x-axis is basically the duration of your reaction. You're going to start off with your reactants, and then you get your activation energy coming up here, and then you end with your product. And I'm drawing this like this beforehand because I know it's an exothermic reaction, so I know my reactant is going to be higher. I have more energy in my reactant than my product in a exothermic reaction because energy is being released from the system. So that's why I can kind of already do that. Now let me get the values. So the reactants start at 850 kgs, and then the activation energy, it's 525 kilojoules. So we're gonna add, so that's gonna get us to our peak of our activation energy. So we need to add 850 kgs plus 525 kJs, I'm sorry. And that gets you 1375 75 kilojoules. 1375 kilojoules. And then it says that the product ends at 125 kilojoules. So boom. I like to do this because it shows us, it helps with this part. This, I can put an arrow right here. This represents our activation energy, which in this system is 525 kilojoules. And then the change in E, delta E, is right here. You get 850 kJs minus 125 kJs. 850 minus 125, you get 725 is your delta H. Because that's basically going from our products to our reactants. Oh no, sorry, I flipped these. Reactants to products. Reactants to our bottom at the end is products, right? I believe that's that. What else does it say to do? Be sure to label. Yeah, that's everything for that, right? 125 kilojoules. Okay. Now let's go on. Oh yeah, and by the way, this proves that this is an exothermic reaction because we're doing technically, I'm sorry, I messed up again. I apologize, Professor, Doctor. It's technically 125 minus 850. And that's where you get 725 negative kilojoules, which is the delta H. This negative means that energy is being released from the system, which basically just reconfirms that it's an exothermic reaction. Let's go to C, the enthalpy of the reaction. Oh yeah, so this, there's really no work to do here because it tells us, calculate the enthalpy of the reaction of the burning marshmallow, assuming that the marshmallow is basically all sugar. It tells us that sucrose has a standard enthalpy of combustion of negative 2,221.2 kilojoules per mole. So there's really no work to do for that, I think. I don't know, maybe I'll get that one wrong, but it says that there. So I didn't really know what to do for that. Apologize, doctor. Please don't talk me too much. I'm just gonna move on to the next one, which is D, which is figuring out the mass in grams of marshmallows. So we want to find out how many grams of marshmallow could be burned, essentially, if we release 89,250 kilojoules of energy. So first, we need to find the amount of moles. And we do that by taking the given value of 89,250 kilojoules, and we're going to divide that by the other given value of 220, what the heck, I'm sorry, it's so late, 2,221.2 kilojoules per mole. I apologize for that. Here these units cancel out, and this gives us, I put this on my calculator, 9,250 divided by 2,220, oops, sorry, just putting this in the calculator, 89,250 divided by 2,221.2, you get 40.18098. Let's round that to just 40.18 moles. Next, now that we have our moles, 40.18 moles, we need to find the molar mass of sucrose. That's what I'm going to use here. My what's this called? Periodic table. So the equation for sucrose is C12H22O11. So we're gonna use C, which is obviously carbon, which is 12.01 times how many? Times 12 of those. And then H, I know that is 1.01. Oh, sorry, you couldn't even see me. 1.01. And there are 22 of those, I believe. Yes. And then finally, oxygen, I know is 16.00 on the dot, and there is 11 of those, times 11. So if we do these individually, you get 12.01 times 12 equals 144.12. And then you gotta do the same over here. 1.01 times 22 equals 22.2. I should have known that off the top of my head, but sorry. 16 times 11 for our final value gets 176. Now we're gonna add these all up, plus, put that in, 144.12 plus 22.2 plus 176 equals 342 0.32. And so basically we need the molar mass of sucrose so that we can multiply it by the amount of moles of sucrose that we have in our current system, I think, right? Yes, times 342.32 grams per moles. So now we can cancel out moles, and this gives us our mass. This just gives us grams, which is what we're trying to find, because it's asking for the mass of the marshmallow burned. So this represents the moles of marshmallow burned. And yes, right? Because yeah, we divided by the delta H from the amount of energy. Yes, this makes sense. Equals, let's put that into a calculator. 40.18 times 342.32 equals a really big number. What the heck is that? 13752.4, I think. Yes, you get 13,754.4176. Does it ask for it in, what does it ask for? It gives us 89,250 kilojoules, so I'm gonna put this in, oh, but this is grams. Should I put it in kilograms? I don't know. I think I will put it in kilograms just in case. 754.4. To put it into kilograms, kilo is basically 1,000, so you just move it 1, 2, 3, and then that gives you 13.75 kilograms of marshmallow that could be burned. Boom. Sorry, that sounded a little convoluted. I hope I explained that well. Hopefully give me full credit for that. Now let's look at the second to last question. 4.55 gram marshmallow is burned and heats up to 1.52 kilograms of water from 25 to 32.5 degrees Celsius. So here we're going to use this equation. Q equals MCAT. That's how I always remembered it. Basically here, Q is what we're solving because we're given everything else. The mass, here we have to be careful because it gives you the mass in kilograms, but we need to do it in grams. And the 1.52 kilograms of water. Yeah, that needs to be grams, I'm pretty sure. So you're given 1.52 kilograms, but because in like this equation, you have to use grams, we have to change this to 1, 2, 3. It's equal to 1520 grams. So Q is equal to 1520 grams. Calculate the enthalpy of the combustion reaction. Yes. Okay. Q, and then C is the, oh shoot, what's that word called? It's the specific heat of the substance, and we are given the specific heat in this case being 4.184 joules per gram Celsius, something like that. That's what it says. Times 4.184 joules per gram times Celsius. And then finally the change in temperature. So we know the temperature goes from 25 degrees Celsius to 32.5. So you simply divide or subtract these two, and that gets you 7.5 degrees Celsius. Right? Now you just multiply all these values together, and then you're going to get your enthalpy value. Right? That's the heat. I believe that's it. So now we can just multiply all these bad boys together, and we're going to get the enthalpy, which is what Q stands for, by the way. I hope 1520 times 4.184 times 7.5 equals 47,697.6. I believe. Yes. And that's in joules. That's the denomination. Does it say to put it in joules or kilojoules? It doesn't say. So I believe that means it's up to our discretion. So we're gonna leave it as that, or we gotta watch for sig figs. Oh shoot. Oh, I think it's 3. Actually, I'm just gonna do kilojoules. 1, 2, 3 equals 47.7 kilojoules. And because, almost forgot, this is an exothermic reaction, heat is being released from the system. Your delta H, you always have to make sure that you got to watch out for the sign, because this basically just tells you whether heat is being absorbed into the system or exiting the system. In this case, like we said over here, this marshmallow is burning, releasing energy, so it's negative, I think. Finally, we have to find the specific heat of a marshmallow, I believe is what we're doing. Right? Calculate specific heat of the marshmallow when 621 kilojoules are added to a 4.5. Okay, this is pretty easy. So basically, we use the same Q equals MCAT equation, but instead of finding our Q value, we need to find our C value, because this represents specific heat. Super simple algebraically. Divide M and change in T by both sides, so that you get C equals Q over maths. Okay. Yes, because this is gonna allow us to find our specific heat. It is given to us that the Q value is 621, I think. Yes, 621. Oh, but that's kilojoules. So this needs to be in joules. So we do our little trick again of 3 decimal places. So you get 621,000 joules. Save myself there. Over with a mass of 4.55 grams, already in grams, times the change in temperature. It is 7.8, right? Yes. Calculate the marshmallow. Yeah, rise at 7.8 degrees. Super easy. Degrees Celsius. That's that, right? So now we... Oh, that is so crazy. 621, 1, 2, 3, divided by 4.55 times 7.8, and you get a value of, whoa, that doesn't look right. Wait, what? 4.55 times 7. Oh, I think I just inputted this wrong, because that definitely doesn't, that looks more right. Yes, that definitely looks more right. So you get a value equals 17,497.88. And this is where we get that unit of joules per gram times Celsius. I did that like connection, just sorry, that has nothing to do with the test. It just came into my mind right now why it's this units. So yeah, the marshmallow has a very high specific heat. That's that, I believe. Do we need to go one less decimal place? I think we're good. I think that's our final answer. Do I need to do anything else? Thanks for watching the video, I guess. I hope that's it. Yeah, thank you.